So that's it. I mean, this is, if you want to solve fully coupled transient poral mechanics, this is the set of poral elasticity, rather. Remember, this is small deformations. This is the finite element model for the linearized or the small deformation theory, right? Remember, we derived the full nonlinear theory, finite deformation, but then we said, okay, we're going to linearize it, and these are the equations we're going to solve later in the class. So now we're back to them, and this is what they look like, full transient, okay? We can make a few simplifications. You know, a lot of time in earth sciences, whether it's, you know, anything to do with soil, hydrology, petroleum engineering, the inertia effects are relatively small. If you're doing earthquakes, it's not, right? So if you're doing earthquakes, you pretty much have to solve the whole thing there. But for you know, most of the things we'll be interested in, we can ignore the inertia terms. This first guy, right? The inertia on the solid mechanics. There are a couple of additional simplifications. If you're a civil engineer, who else is any civil engineers? Right, so you've taken geotechnical engineering courses. You probably know drained and undrained, right? So the drained and undrained limits. So drain behavior, this is a good approximation for sands and gravel, or, you know, anything that's got a high permeability. So in this case, the fluid flows through the matrix free, you know, quite easily. And so this is called the drain behavior. And in that case, we can simplify the equations. Like this. Does anybody see anything special about those equations? Are they coupled? They're uncoupled, right? So this makes it really easy. You just solve the second equation.